Good morning and welcome. Glad to see you here. Not all are on excursion. So we interrupt the pensum for today, and the idea is also for tomorrow to go through a few exercises which are somehow related to the exercises that we have been doing. In some points I go a little bit further, so that's some extra information that you get. And in some cases you get feedback on the classical exercises that we did, and it will generally be a repetition. So today I have 3 points regarding the total error, sum of rounding error and truncation error. That is one. And the other is the stability of ODE methods. And the third is regarding the convergence of a finite difference method for the heat equation. So let us start. So the goals for today and also for tomorrow is to have some repetition of the material. We'll have a more thorough repetition or a summary of the course in the last week. Then I would like to give you some feedback on the exercises, and you're also welcome to ask me if you have you want to know anything more about the exercises. And there will be some extra, so which goes beyond the pensum actually. So let's start with the first exercise that we want to go through. And that is related to the total error of finite difference approximations. So I write this acronym, finite difference approximations. And I would regard this as something extra. If I remark this here, so this is something extra that is going beyond. But it's interesting, I think. You'll see. So the task is the following. That's related to exercise 1. Consider the function that we also considered there. F of x is equal to the tangent of x at the point x equal to 1. And we want to approximate the first derivative of f with respect to x by the central finite difference method. Following. We use here this notation. We say df of h, that shall denote the ratio of f evaluated x plus h minus f evaluated x minus h divided by 2h. So h is the grid spacing. And we want to do that on a floating point system. That is on some computer using some programming language. In our case it would be MATLAB, but you can use any you like. So on a floating point system. And we are supposed to use both single and double precision. So the task of the exercise is find the grid spacing h for which the modulus of the total error, that is the absolute value of the total error, of this central finite difference approximation, df of h, is approximately minimal. So we don't want to have it really fully accurate, that would be too much, but approximately minimal. So that is the task. And to remind you what this is up to, I recall exercise 1. And there we had this picture that you generated in the first exercise, where we had here the grid spacing h, and here we had the error, and that was the error, relative error. So it was the error of the finite difference approximation minus the exact derivative of the tangent of x at x equal to 1 divided by the exact derivative. And then we had different approximations, and the ones that we were mostly interested in were the first and second order methods. And let's see, where are we here? Let's see, we have the second order, for example, is here. Here we have the first order. And what is happening, that is, here the error is governed by the truncation error. So it goes down either with h squared or with h for the second or the first order methods. But then at some point, and that is the point that we want to determine, for example here, we want to find out where is the h, where this curve, which contains both the truncation error and the rounding error, is minimum. Because at some point the truncation error is no longer important, but the rounding error gets important. For example, here we see it goes up, it is jagged, because sometimes the truncation error works to our favor, sometimes not. But nevertheless, there is a curve here which has a slope actually with 1 over h, not h or h squared, but 1 over h. So the error gets larger. And the task is to determine this location of the h where this happens. So it's not so, well, we'll find out. Let's see. We are interested, we are looking now for this here, for the double precision that is here, the red curve, and we are also looking, oh, the curve, that is something that is interesting here. The picture is not totally on it. Okay, now we have it. Now it's better. So it is 10 to 0, minus 2, minus 4, minus 6, minus 8, minus 10. And we shall then focus on this curve here, try to find this location where we have the minimum h of the total error, and also for the single precision we have here. So you see here with single precision the rounding error takes over much earlier, because well, we have only essentially half of the digits to represent the numbers, and the rounding error then occurs much earlier, so we have a lower h for the minimum. So that is the goal, to determine this. So how shall we do that? First we will set up the total error, and then we look at both the truncation and the rounding error, and look where this curve is minimum. So the solution to this exercise is the following. First we look at the total error. We denote that as epsilon total, and that is I use now this notation. This is the floating point computation of the central difference approximation. Because that is now important. If we would do this computation on an ideal computer, which did not have any rounding error, then we could forget about that. But we have that. We cannot do it otherwise. We have to represent our numbers by a finite number of digits. So that we have to use floating point, otherwise we can come up with something new. We're welcome to come do that, but at the moment we have only floating point systems to do computations. So then represent this approximation then on the computer as a floating point. And the error is then the difference with respect to the accurate first derivative at the point x. So, and then I write also what this FL means. FL of something means floating point approximation. So that is what we compute with our laptop or PC or whatever we are using. Floating point approximation of the something. Here it would be the central difference approximation. So then we write now the total error a little different. We try to involve now both the rounding error and the truncation error. So that means we write now simply the floating point of the central difference minus the central difference. So then we can focus here on the floating point on the rounding error. And then we have also then the difference here between the finite difference approximation and the exact first derivative. So that means we then have here the rounding error due to the fact that we are using a floating point system, and here we have the truncation error. So we'll use the notation for that as epsilon rounding error, and here we have already a notation that is the truncation error at the point x with the grid spacing h. Okay, so then we now look at these two individual parts, the rounding error and the truncation error. So the first thing is to start that we look at what is the floating point representation of our finite difference approximation. Then we write it simply. So then it's we are going to look at. And now we make a simplification here that we say, okay, instead of looking at all the floating point errors that we do, we concentrate on the floating point error that we do to compute this and to compute this. We also have one when we take the minus, when we take the divide. But we approximate this now by just looking at the floating point error, computing the f of x plus h and the floating point floating point representation of f of x minus h divided by 2h. So ignore here that we also have floating point errors when we do the minus and when we do the divide. The 2 is not a problem in a binary system, and if h would be a power of 2, then the divide by 2h would be no problem. We could do that accurately on the computer. But we focus on this. And then we note that we can write the floating point representation of, say, this function f of plus of x minus h as the correct representation f of x plus minus h times 1 plus the relative error. That is the relative error of f of x plus minus h. So that is just another way of expressing things. And this relative error, we can write the following way. F of x, I write it now just for f of x because it's similar for f of x plus and minus h. So the definition of that is that it is the floating point of f of x minus the correct f of x divided by the correct f of x. So the relative rounding error of relative rounding error of, in that case, it would be of the function f of x, the function value f of x. And now we can actually compute this and give an approximation to that. And that relates to the propagation of errors. Have you been up to that before? Error propagation in some class? Not? Okay. It's also important for measurement techniques. So how also here we look at rounding error, how they spread, but it could also be important to see how measurement errors spread. So because we get the following. We have the epsilon. Let's see, we continue our discussion there. So the floating point of x of f of x minus the f of x, that is divided by f of x, that we can write in the following way. We can say that is the function f that is evaluated not at x, but it has some error. Epsilon x is the relative error of x. So here we look at the floating point representation of x. And then we have here, say we have the correct f of x, and we divide by f of x. So in here, the epsilon x, that is the relative error. So that is the floating point of x minus x divided by x. So that's the relative error of the representation of the number x on the computer. And for that, we know something. So that is the rounding error of x. Let's see. So that is the rounding error. This that we have here is the rounding error of x. And we know that this absolute value of this relative, it's the relative, sorry, it's the relative rounding error. Relative. So here, relative rounding error of x. And we know that this in absolute value is bounded by the machine epsilon of the computer. That is what we know. So that is then how we express the floating representation of x here. And now we just concentrate on this here. Let's see. Here I think I should make a point because here I made an assumption. The floating point of the function of x is here, I just represent it as the function of the floating point of x. So this is an approximation. Because when we compute the f, we will also have floating point errors. But here we only concentrate on the consequences of computing the function f with a floating point, not with the exact x. So that is then the approximation that we do here. And what we can do now here, that we can always, if we have a smooth function, we can do Taylor expansion of this. So here, so we continue with this, so this is now, this is then equal to, and we do now Taylor expansion. Here, and then we get f of x, and then we get x epsilon x times the first derivative of x, and we get higher order terms. So the next one would be then the x epsilon x squared half, second derivative of x plus and so on, minus the f of x. So that is, we do a Taylor expansion of this here. So it is f of x plus x epsilon x. So that we can do. And we divide by f of x. And then we see, when we do that this f of x, this cancel. And if we neglect these higher order terms, because we assume that we know that epsilon x is very small by this, so we say we can neglect that, then this is approximately equal to x epsilon x times the first derivative of f with respect to x divided by f of x. So thereby we have now an approximation of the relative error of the function f of x. So we were starting here, and then we made this approximation that it is only the propagation of the floating point of x that is important, not the individual operations doing the function. It is only the error propagation, and then we find this. So then we can now look at the rounding error by this, because we know now how then we can represent the floating point of f of x plus h, if we know how we can do it for f of x. So you see, when we want to know that, then we can represent that with the exact f of x plus 1 plus the relative error. So this is now what we are going to do. We are looking at the rounding error. The rounding error of our finite difference approximation. And then again we make the approximation that we look at the absolute value. We make the approximation, we have the 2h, that we just look at the floating point of f of x plus h, and then to get the error we have to subtract the correct f of x plus h. So again we focus only on the floating point errors due to the function representation, minus, and then we will have here the floating point of f of x minus h minus the correct f of x minus h. That is the h here. Okay, so that is this bracket here, and then the absolute value here. And now we use what we have been doing here. So here we have the floating point error, and then we can use the formula that we have derived here, that we can represent this as the relative error of the function times the function that we want to represent. So that is then approximately equal 1 over 2h, and then here we had the formula for x, here we need it for x plus h, and then we have here the f prime of x plus h, and we have the relative error now of x plus h. So that is what we use here. We use that our relative error for the function that we derived here is approximately equal to that. And so, yes. So then we have that. So you see here, then what we are looking here at is this error here, then is approximately equal to what we have here. And that we apply here not to x, but to x plus h. So then we get this formula. Similarly, we get the formula for f of x, the floating point error of f of x minus h. That gives then x minus h, f prime of x minus h times epsilon x minus h. So then we have that. And now we make another approximation that we say, well, h is small, so we neglect that. Here, 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 and here. But these epsilons here we keep, because they are rounding errors, and they round sometimes to our favor, sometimes to our unfavor. And they are just, we know of them that they are just bounded in absolute value by the machine epsilon. That's all we know. So then we can say the following. This is then approximately equal to 1 over 2h. And then we make this approximation that we say we take here x, and here we take f prime of x. And here we take the relative errors as they appear, and that we cannot control actually. Well, there is something happening, and that is more or less out of our control. But we only know that they can be plus or minus. The only thing we know that they are bounded by machine epsilon. But what we can do at this point is that we use triangle inequality to make estimate this absolute value. So what we use here is then the triangle inequality. That means we can use then the absolute value of x, f prime of x divided by 2h. And then here we can individually use the absolute values, epsilon of x plus h plus epsilon of x minus h. So then you see what we do is we take the absolute value of that plus the absolute value of minus this. In any case, we can estimate those with machine epsilon, so we can estimate these two here together by 2 times machine epsilon. So from that, we get then the following estimate. So first, let's see, maybe we can do that still here. So we continue this inequality over there, and we say this is smaller equal absolute value of x times f prime of x divided by 2h, and here those then are estimated by the same argument as here, by 2 times machine epsilon. So then we can factorize the 2, and then we have an estimate of the rounding error. Again, we have only taken into account the propagation of the rounding error of x. We have not taken into account individual errors in computing f. But this is already something useful what we have done here, as we shall see in the end. So now we have here estimates, but nevertheless we estimate now the rounding error, modulus of the rounding error, its absolute value, by the estimate that we came up in the end, which is the absolute value of x times the first derivative of f with respect to x divided by h times machine psi. So that is our first result that we shall use to represent the rounding error. Now, having worked now on the rounding error, we focus now on the truncation error. So that is a field that we are more familiar with. And that is something that you have done and I think you are quite comfortable with. So that then just a repetition of what we did in exercise 1 to understand that. So we write down now the formula of the centered difference approximation, and the truncation error is then minus the exact first derivative. And then we do Taylor expansion. So we assume f is now the exact function, and then we do Taylor expansion. So, let's see. We have f of x plus h f prime of x plus h squared half, second derivative f with respect to x plus h to the power of 3 divided by 6, third derivative plus higher order terms, and the same thing for f of x minus h, and then we have f minus h, f prime of x plus h squared half, second derivative of f with respect to x plus the third h to the power 3 divided by 6, third derivative of x plus higher order terms, and divided by 2h. And then we see we get here f of x cancels the second derivative cancels, and we get here h and h 2h, so we get again f prime of x, and this we get twice. Let's see, here is an error. Here's an error, sorry for that. Here's a minus, because here we are an odd, so here we have a minus in front of the third of the h to the power 3 times the third derivative. So we get then 2 times this term divided by 2h. So in the end we get then, let's see, I've forgotten one thing. Now we have taken into account everything regarding the finite difference approximation. But to get the truncation error, we have to subtract the exact first derivative. So this problem, that. So we have then here minus f prime of x. So that is what we have to take into account. Now we were looking at this and we found that we get the third derivative term here twice. And we end up by getting here then this h to the power 2 divided by 6 times the third derivative of f with respect to x plus higher order terms minus the f prime of x. This comes from here. So, and from that we see that we end up with the second order term, as we should for this central method, which is second order, we know that. but here's just the confirmation. So then we have this. And now we shall approximate then our truncation error with this term. We neglect the higher order terms, and then we use them for the approximation of the truncation error, then simply this. So from that we get, that is our formula 3, that the absolute value of the truncation error at point x with the grid spacing h is approximately equal to h to the power 2 divided by 6 times the absolute value of the third derivative of f with respect to x. So we neglect the higher order terms. And now we have derived everything to get the formula for the total error, because we have now derived formula for the rounding error that we did before, and now just repetition of what we have done before, the truncation error. So now we can get the total error. So using this formula 1, 2, and 3, we get that the total error is approximately equal to, and now we take then what we have over there, that is x times f prime of x divided by 6, no, that was h, sorry, h times the machine epsilon, it's the rounding error, and we have now the truncation error, which we have here, which is h squared divided by 6 times the third derivative of f with respect to x. So that is our formula that we get. And then we use, the important thing for us is now the relation that we consider this now as a function of h. So we define this, then we define our function, we define the minimum as g of h. We define that by, in this sense here, as a over h plus b times h squared, where the a is then what is coming from here, that is then the x f prime of x machine epsilon, and the b is then coming from here, that is then the third derivative of f with respect to x absolute value divided by 6. So because then we can more easily do the analysis with this function. Now we have to minimize this function. This is an easy task. We have the minimum for the g prime of h equal to 0, and we have to check that for this minimum the second derivative of h is greater than 0. To be sure that it is a minimum. So then we just do that. So the g prime of h, that turns out to be minus a divided by h squared plus 2bh, that is equal to 0. And from that we get a formula for our h. H turns out, take that as number 4. That is then, see, we just bring that on the right hand side. We multiply by h squared, or let's see, yeah, and then we get that h is equal to a divided by 2b to the power 1/3. If we insert our a and b over there, we find that this is then x f prime of x times machine epsilon divided by the absolute value of the third derivative of f with respect to x. So we have then a 2 in the denominator, but we have also here the 6, which will come in the numerator then. 6 divided by 2 is a 3 then, so we get a factor 3 in here. And that is then taken to the power 1/3. So that is our formula. So here, so we have just to check that it is a minimum. So the second derivative of g with respect to h, we do the derivation, is 2a divided by h to the power 3 plus 2b. And a and b are all greater equal 0, so we assume now that some of them is not, so that they are not all at the same time 0. So because x could be 0, f prime could be 0, one of them, and this. So we assume that this is, that we have this unlikely situation is not the case, so that this is then in fact greater than 0, unless the x f prime of x is 0 and the f third derivative. So then we could not, then it would not be clear, but we assume that we have one of them is not 0. So that is our assumption. Then we have a minimum. So now we can use this formula for our case, the f of x is equal to tangent of x, and for x equal to 1. Then that yields the following. A, h is approximately equal, so 2 is put in all the numbers. We find out that this is 2.72 approximately. Let's see. Sorry, I start with a single precision first. 2.21, 10 to the minus 3, and that is for IEEE single precision, and the machine epsilon for this standard, so that's a standard of the Institute of Electronics and Electrical Engineers, IEEE. I have set this standard, and the standard is that this is equal to 2 to the power minus 53, which is approximately 10 to the minus 16. Oh, sorry, this is wrong. This is the double precision. It is, I think I have to check that. I think I wrote it down. Yes. This is approximately 10 to the power minus 8. So that is because that is entering in our formula here. 5p, h is approximately equal, and that is then now 2.72, 10 to the minus 6 for IEEE double precision, with machine epsilon being here, that is what I wrote before, that is 2 to the power minus 53, that is the length of the mantissa, how many digits, the binary digits we can represent, and that is approximately equal 10 to the minus 16. So Yeah, so that is our result. Then we can check now how well that is in agreement with what we observed in the computation in exercise 1. So let's see. So let's take the single precision first. So it's 2.2 10 to the minus 3. We have 10 to the minus 2 here, 10 to the minus 4 here. So 10 to the minus 3 is approximately here. It's a little bit larger, so that might very well be around here. So where we have the minimum. The jags we cannot predict. They are unpredictable, but we approximate everything just by a straight line. So, and that seems to fit quite well, so that we get roughly the right value of h, where the minimum of the total error is for single precision with double, using the second order difference approximation for the first derivative. For double precision, we have the red curve. See here, double precision second order. We have this curve here. And then we get down here, which is minus 2, minus 4, minus 6. So it's a little bit larger than 10 to the minus 6, where the minimum is. And that is fitting also quite well with what we get here, 10 to the minus 6. A little bit more, and that is also what we observe here. So from here on, we have then that the error increases with 1 over h. That is because of the rounding error. So that means we can conclude that our analysis predicts quite well what we observe in the computations. So the minimum of the total error by our analysis is predicted quite well. Okay, so we stop here for a 15 minutes break.